Hello and welcome. In this video session, we will begin a new topic on signals. Signals are like the interrupts that occur when the program is running. These interrupts are asynchronous events. This means we are not sure when the interrupt occurs when the program is running. So, synchronous events are those in which we know the occurrence of the events, but asynchronous events are those in which the user or the program is not aware of the events timings in which they occur. So these asynchronous events are called as like a software interrupts. So these signals can originate from outside the system as well as within the system. The example in which the signal can generate outside the system is, let's say we are running a program, and when the user enters a sequence of characters from the keyboard like Control C, then we are in fact sending a signal to the process. So this is an example of a signal that is being generated from outside the system. In the same way, within the system also, the kernel generates the signals and processes it to the desired process. So the signals are identified by a unique number in Linux systems, and each signals has their own way of handling the signal. So a signal has a very precise life cycle. The signal is raised first, the kernel stores the signal, and at appropriate time it delivers to the required process. The process, once it receives the signal, it handles accordingly. There are different actions that can be taken by the process for each of the signals. So all the signal by default has a default action. Let's see more on this. So a kernel can perform one of the three actions depending on what the process is asked to do. Example, the process can ignore the signal, that is, the process can behave as if the signal has not occurred at all. But there are two signals that cannot be ignored. They are SIGKILL and SIGSTOP. So these signals cannot be ignored. Then next, the process can catch the signal and handle the signal accordingly. So whenever the process gets the signal, there is a handler written for each signals. So whenever the signal has a dedicated handler is nothing but a function that will be called when the signal arises. So if a particular signal handler is present, the execution jumps to that handler and executes the code that is given in the handler, then returns back to the main program. Let's see this for more example in the next slide. Then we have one more action, that is performing the default action. So performing the default action means whenever a signal comes to the process, and if there are no signal handlers, then by default every signal has a default action to be performed. So this is the three different ways in which the process can look at the signal. The first one is like ignoring the signal. The process can either ignore the signal or handle the signal or perform the default actions. So all these three things is controlled by the code. Now let's see how a signal handler works if a signal is being handled. So let's see this case. That is, we are writing a separate signal handler for a specific signal. So in this case, we can see that we have a main program running, and these are the different instructions that are running, and we have a dedicated signal handler. So by signal handler, we mean that there is a dedicated function that will be called, and it has a code instructions inside that. So let's say that the main program is running and the signal can occur at any time. That is why we call it as a asynchronous event. And when the signal is delivered to the process from the kernel, the current instruction will be executed, and then it jumps to the signal handler, and then it executes the signal handler code and returns back to the main program. So this is the general life cycle of a signal handler. A signal is being identified and it has a prefix of SIG. So all the signals has a prefix of SIG. For example, a signal SIGINT has a prefix of SIG, and this is raised, SIGINT is raised usually when the user presses a Control and C on the keyboard, and all the list of signals is being defined in a header file called as signal.h. Now let's have a look into the signal list. From this diagram is taken from the signal.h header file. Here you can see each signal has a unique number. For example, SIGHUP is assigned a number 1, SIGINT is assigned a number 2, and it goes on. So each signal has a unique number and it can be identified either. So for example, either the user code can call it as a SIGTERM or using the number 15. So both are interchangeably used. So as we have discussed in the previous slides that every signal has a default action. For example, we have shown here that the signals will have a default action. That means if a signal does not have a signal handler written separately, then by default it has a action to be taken. So these are the list of signals on the left hand side and the default actions of every signals on the right hand side. So for example, SIGHUP will have a default action to terminate the current process. The same way, SIG quit will have a default action to terminate the process. Before terminating it generates a code dump and then terminates so that the user can read the code dump file in order to understand why the termination occurred. So these are the different signals and its default actions. So in this list of signal handlers, just for understanding purpose, let's take few of the signals which are more commonly used and let's discuss few of the signals. We will not be going through all the signals, only the few signals we will take as an example and let's discuss it. So SIGABORT is a signal that is being raised when an abort function is being called. So whenever an abort function is called in a process, the process receives a signal called as SIGABORT, and in this case a code dump file is being generated and the process terminates. So as a result of this, the code dump file can be used by the user to debug why the process had terminated. SIGALARM. SIGALARM is a signal that is generated when the alarm function is called and the timer that is used inside the alarm expires, and the signal SIGALRM is called. We can see some examples of SIGALRM down the line. SIGBUS, also called as the bus error. So this signal is raised when the process has a memory access related error. When memory access error occurs, this SIGBUS is called. And we had discussed the SIGCHILD when we had done the parent and child process. So whenever a child process terminates, a SIGCHILD is being raised and delivered to the parent process. SIGCONTINUE. Whenever the kernel wants a process which is stopped to resume, then the kernel sends a signal called as SIGCONTINUE in order to continue the stopped process, and the process will be resumed. SIGFPE is a signal raised in case of a arithmetic execution exception occurs, and there are different similar processes. SIGIL is whenever a illegal mission instruction is executed, SIGKIll is generated, and SIGINT is generated when user presses Ctrl C, and SIGKIll is sent from the kill system call. So we have different signals like this. SIGPipe is used. This is a signal occurred when we have a pipe related operation. So we will see SIGPipe down the line when we discuss about pipes. So signal has two types of user provided signal, SIG user 1 and SIG user 2. These two signals are the signals which are user defined purpose. So user can generate these signals for user applications. So user can send from one process to other process these signals, and so these signals are not raised by the kernel, and user raises these signals. So what we have discussed is only a few subset of the signal. You can go through a list of all the different signals in order to understand each signals in depth. So in next video session, we will be having a look into the code part of the signal and how to handle the signal handlers, what are the default actions, and all this we'll be seeing using the code examples. Hello and welcome. In this video session, we will discuss the programming concept of signal. In order to use the signal system call, we have to include the signal.h, and the system call signal takes two parameters. The first parameter is the signal number, and the second parameter is the function pointer, and this function pointer is nothing but the pointer to a function which takes an integer and returns a void. Also, whenever a signal is delivered to a process, using the system call signal, the signal specified here can either perform a default action or can be ignored for this particular signal. So if we want to ignore a particular signal for a process, we have to specify a sig_ignore IGN in this parameter, in the second parameter. And if we have to perform the default action of a given signal, then the second parameter needs to be specified as SIGDFL, which is nothing but the SIG default. Now let's have a look into the manual pages of signal for better understanding. As specified, the manual page includes the information of the system call signal. We need to include the header file signal.h, and signal is the system call which takes two parameters. The first parameter is the signal number for which we are handling the signal, and the second parameter is basically type defined to a function pointer which takes a integer as parameter and returns void. Also, when the signal system call fails, it returns an SIG error. Now let's see the system call called as kill. This system call kill is used to send a signal to a particular process. For example, this is the header file that needs to be included in order to use kill, and the system call is KILL, and it takes two parameters. The first parameter is the process ID, that is nothing but to which process the signal needs to be sent, and the second parameter is the signal number. So for example, let's say we have several processes running, and if we need to send a particular signal to a particular process, then we need to make use of this kill system call, and we have to specify the process ID of the particular process and send the desired signal. We will see some examples of both this signal and kill system call for better understanding. Let's have a look into the example. In this example, we will see how to handle the signal. Here we include the required header file, and in the main program we begin with displaying the process ID using get PID system call. Then let's say we have to handle a signal called as SIGINT and SIGTERM. SIGINT is when we press a control C, the signal SIGINT occurs. And so now we are specifying the function which needs to be called whenever a SIGINT occurs. Similarly, when a SIGTERM occurs, also we are calling a function called a signal handler. Signal handler is nothing but a function which takes a integer, that is nothing but a signal number, and returns a void. So based on the signal number takes the signal number of the particular signal. So let's say if SIGINT occurs, then this function is called with sig number equal to SIGINT. And if the signal SIGTERM occurs, then the execution will be jumped to the signal handler and the sig number will have a value equal to SIGTERM. So this program continues in a while one as we have specified here. Let's compile this program and see the output. Now let's compile the program initially. So we have compiled the program and let's run the program. Okay, now the process ID is 31806. As we have mentioned here, we are handling the signal SIGINT and the signal SIGTERM. So in order to generate a signal SIGINT, let's press Ctrl and C in the keyboard. After pressing Ctrl and C in the keyboard, we have got this output. So after pressing a Ctrl and C, this process which was running, it got the signal SIGINT. And since we have handled the signal handler, it jumps to this function and this particular print is called and we get this output caught SIGINT. We get this caught SIGINT. Then since we are exiting from the process by using exit system call, the process has ended. Now let's say we don't want to give an exit, and now if we comment this code and compile this and see, let's see the output. Now we'll run the program. So now if I press Ctrl C on the keyboard, let's see the behavior. So pressing Ctrl C has raised the signal SIGINT. It jumps here, it prints the line caught SIGINT, but if you can see, it has not ended the program. So next time when we press Ctrl C, once again we can see the same behavior. So any number of times the signal is caught, it jumps to this signal handler and takes the action whatever is specified within the signal handler. As a note, it is a good practice to not to override the default action of the signal. For example, the SIGINT by default terminates the process. So we have to handle the signal and perform the appropriate action, and then we have to terminate the process. So as a general practice, this would be a proper use case. Let's see the next set of examples. So here, let's see how to ignore the signal. So in this case, we include the required header files and we have written a signal handler. So the execution begins with the main function, and in this case, let's say whenever we have a signal called as SIGINT, that is nothing but the Control C, we have to ignore the signal. So when we ignore the signal, then the process behaves as if the signal has not been delivered to the process itself. So this signal will be ignored and no action will be taken in case of SIGINT. But whereas in this, the SIGTERM we are handling with a signal handler, and whenever a SIGTERM signal occurs, it jumps to the signal handler, and this particular else if condition will be executed. Let's compile this program to see the output. GCC to let's compile it. Now we have compiled the program. Let's run the program. Okay, now the process ID is 32466. Now I'm going to enter Control C on the keyboard. Now even after entering Control C, the program did not jump to anywhere. So since we have specified signal ignore, this particular signal, the SIGINT that is from Control C is being ignored. So now let's see what happens when we give a signal SIGTERM. So if we go back to the presentation what we had discussed, the SIGTERM is nothing but a signal with a ID 15. So now let's see how to give a signal SIGTERM to this running process. Now the program is running and the process ID is 32466. So now let's give a signal. Let's copy the process ID here. So in order to send a signal to any process, a kill is used. So kill followed by, this is a command, shell command in order to send a signal to particular process. So here kill space the signal number followed by the process ID to which we are supposed to send the signal. So in this case, after executing this, we are going to send a signal called as SIGTERM to the process 32466. So now just observe the output after sending the SIGTERM. So we have sent the SIGTERM, and in this process the SIGTERM is being caught. So it's nothing but the SIGTERM is being caught because we have specified the signal handler, and this signal handler jumps here, and this particular print is seen on the screen, and we tend to exit the program by giving a exit success. So this is what it has happened here. So the point we have to note here is, in order to send a particular signal from outside the process, we can use the command line kill, and it takes the signal number followed by the process to which it has to be reached. So in this case, let's say that now if we give this SIGTERM instead of the handler, let's say now I want to ignore the signal SIGTERM. So now both SIGINT and SIGTERM are ignored. So let's compile this and see the output. Now let's run the program. So now the process has a ID 32525. Let's again generate SIGTERM to the process 32525. So let's observe the output now. Now we have generated a SIGTERM, but if you see here, the SIGTERM is not being caught in the program. This is because we have ignored the signal SIGTERM. So the signal with number 15 corresponds to SIGTERM, and because we have ignored the signal, the process is ignoring the signal SIGTERM. Now let's say we enter Control C here. I'm entering Control C from the keyboard. So even after entering Control C, we have not got any, because of the signal ignore, we did not get any signal. The signal is being ignored. Now let's say that we comment the complete code from here, #0 to this code. So now let's demonstrate the default actions. So by giving a #0 and endif, we tell the compiler not to compile this part of the code. So this is a preprocessor directive. So #0 to #endif, this particular code will not at all be compiled. So now what we are doing is we are just giving a dummy main function and it just waits in a while one loop. So let's compile the program. So now let's run the program. Here the process ID is 1293. So now if we give a control C from the keyboard, then since we are not using any signal handler, we will be getting the default actions. So now the default action of control C, that is nothing but a SIGINT, is to terminate the program. In the same way, now let's say we generate a signal called a SIGTERM by, so let's give the process ID of this 1312 is the process ID. So if we press enter, we are going to give a SIGTERM to this process. Now let's see the default behavior of SIGTERM. The process is terminated. So the default behavior of the signals depends on each of the signals. So each signals will have its own default behavior. Now let's see the next example. So here in this example, let's see the default action. In this case, we have the signal handler and the main function starts, and for the signal SIGINT, whenever we specify the SIGDFL, that means we want the default action of the particular signal to be taken. For example, let's say before the program we had a SIGINT and we have specified a signal handler, and now let's say we want the default action of the SIGINT to take place. So specifying the signal name and the SIGDFL will reset the signal handler and the default action will be taken. So let's compile this program to understand. GCC. Okay, now let's run the program. Now if we press Ctrl C, so now the default action is being taken place. So whenever we have used a signal and we have handled some signal handler, and if at any point of time we want to make sure that a particular signal, its default action will be taken, then we can specify this SIG_DFL. So in this case, the SIGTERM is not altered, and whenever a SIGTERM is called, it jumps to the signal handler. Now let's see the next set of examples. Now let's see an example of the signal called as SIG alarm. So here the SIG alarm is used, and the signal handler is, in this case we are using a function called as display message. Whenever we call a function called as alarm, we have to specify the time in terms of second. So as soon as the timer expires, a SIG alarm signal is raised, and in this case, since we are giving a handler, it jumps to this function, and whatever is within this function will be executed. So in this case, what happens is we have given a signal handler to the SIG alarm signal, and after 2 seconds it jumps to this functions, and prints this, and then again we are setting a 2-second alarm. So what happens now is, for every 2 seconds, a signal called a SIG alarm is generated and it keeps on jumping to this signal handler. Let's compile this and see the output in order to understand the program. Now let's execute this. So if we observe the output, for every 2 seconds, it is jumping to the signal handler. So in the signal handler, we are again giving the alarm function. Now let's see what happens when we change the code here. Now let's say we are not generating any alarm within the signal handler. Now we can give a guess what can be the output of the program. So what happens in this case is, after 2 seconds, because of this alarm, the signal alarm is generated and it jumps here, and after this it prints this, and it let's see, after 2 seconds it has printed SIG alarm. Since now we have not given any alarm, so now it is in a while one loop and it is executing the while one instruction forever. Now let's see some more examples. Now let's say that I give a signal ignore. So now let's see how a signal ignore will come in picture. So in this case, what happens is, the main program has given a signal handler for SIG alarm, and after calling alarm of 2 seconds, it jumps here. Once it jumps here, it prints this, and now the SIG alarm is ignored. That means the next time whenever any alarm function is called and a SIG alarm is generated, this particular signal is ignored. So that means this SIG alarm does not cause the signal handler to be called. Let's see the output. So here, after 2 seconds, it has generated a SIG alarm, but this alarm function is working. It is calling, it is generating SIG alarm, but since we have ignored the signal, only once this function is called. So after ignoring the signal, even though the signal is being generated, the handler is not being called. Now let's see what will be the behavior of this when we enable the default. So whenever a default action is present, it generates a SIG alarm and it terminates the program. So in this case, what is happening is, the first SIG alarm, when it occurs, it jumps to the signal handler, that is nothing but the display message. After this, we are giving a default action for the SIG alarm signal. That means the default action of a SIG alarm is to terminate the process. Let's have a look here. So the default action of SIG alarm is to terminate the process. So for the first time, since we are given we have specified a signal handler, it jumps here. Then we are resetting the signal handler and we are giving a signal default. Then whenever a signal occurs due to alarm, it does a default action to terminate the process. In this video session, we will see a demo program, how to use the user-defined signal, SIG user 1 and SIG user 2. Here in this demo, let's communicate between a parent and a child process using SIG user. So in this program, let's open the first program here. This is the program 1.c, and here we include the required header files, and the program begins from the execution of main, and here if you observe, the program 1 has created a fork call, and because of fork we have two process now in memory, that is the parent process and a child process. And if the fork creation is failed, then we exit the program. And if you observe here, the CPID equal to 0, this means this is the part of the child process. The else section is the parent process. So the main thing in this program is after a fork we are doing a executable, and we are doing a executable of a second program. So we have two programs, program 1 and program 2 now. So the child process virtual memory is being replaced by the program 2 now, and just we pass some arguments, argument 1 and 2. This is not required, but just for more demo purpose we are passing some arguments to show how to pass the arguments, as we have discussed this in the previous video session also. So after the executable is successful, we will not be seeing this print because the child process now is being overridden by the new program 2. So in the else part, this is the parent process, and the parent is registering the signal SIGUSER1 with a signal handler, and if the signal returns SIG error, that means there is an error using the signal system call, and we print the same on STD error. STD error is nothing but the output standard error, which is nothing but the output or the screen, and we exit the program. If the signal is successful, it enters here, and now we have registered the signal handler. Let's go to signal handler function. So now signal handler is a function pointer, and the function pointer has been defined here. So here we have to say for which signal we are handling, and as we have mentioned before, signal handler returns void, and if signal number is SIGUSER1 only, then we are handling something. This is just for a demo, so we are just putting some prints based on the different use cases. One can use different program here after this, but this is only for demo purpose, so we are showing that how we are handling the signals. Then later the parent process prints the CPID. The child process created by a parent is, so the child process process ID is being printed by the parent, and then the parent sleeps for 2 seconds. Then if you observe here, kill is the system call that is used to send a signal from one process to the other. So in this case, the first parameter is the process ID to which we are sending the signal. So here CPID is nothing but the CPID or the process which the parent has created, and here it is nothing but the child process, and we are sending SIGUSER2 to the child process. After sending the signal to child process, the program 2 should handle the SIGUSER2. Let's see the program in let's see the code in program 2. So after that, the parent process does a wait. So once we call a wait until the child process exit, these lines are not executed. So once the child process exits, then only these 3 lines will be executed. And here we print the parent ID and the child's process ID and the status in which it is exited. So these are just for reference purpose. So now let's see how to handle SIGUSER2 in the second program. That is nothing but the program 2. So now let's open the program2.c file. So here we have program2.c file, and we include a required header file. And as we have mentioned before, the executable will replace the child's process virtual memory by the virtual memory of program 2. So when the program 2 begins, it begins from the main. So now we have a print saying that whatever we see here, child colon is of print coming from program 2, and the print here parent colon is coming from the first program 1, or nothing but the parent process. So now if you observe here, the program 2 has a signal handler for sig user 2, and the function which will be called when this program receives a signal sig user 2 is signal handler. So this is the signal handler, and if sig number is sig user 2, then we print some message on the screen. And this is just for our reference purpose, that the arguments that are passed from the program 1, these are the arguments passed, even though this doesn't make any sense here. Like we have just showing a demo to say how the arguments are also passed. And then the child process sleeps for 5 seconds. And now the child process also sends a signal called as sig user 1. So this is the child process. The child process sends sig user 1 to the parent process. So get PPID gives the process ID of the parent. So this sig user 1 goes to the parent process, and since it is handled here sig user 1, this function should be called, and whenever the parent process calls this CPI calls the sig user 2 and it sends to the child process, this sig user 2 will be interrupted and it jumps to this execution. So let's say any process, it is executing in some instruction. Whenever it receives a signal, based on the delivery of the signal, the kernel delivers the signal to the required process, and the current instruction whatever is executing will be executed. Then it jumps to the signal handler. Then it does the execution of whatever is specified, the code specified in the signal handler, and it jumps back to the place where it was previously executing the instruction. So now I hope the program is clear. Let's compile this and execute in order to see the output. Let's compile the code. Program 1 we are compiling. Now let's compile program 2 as well. Now we have program 1 and program 2. Let's see this. So we have program 1 and program 2. So let's execute program 1 here. So what we can expect the output is, the program 1 is it is a new process. We can call it as a parent process, and this program 1, it forks a new child, and that child is being, because of SIGKILL, it is being replaced by the program 2 virtual memory. And now we'll be having two processes in memory, the parent process running program 1 and the child process running program 2. And program 1 sends signal sig user 1 to program 2, and program 2 sends sig user 2 to program 1. That is nothing but sending of signals from child to parent and parent to child. Let's execute this. Let this run, then we'll explain the code. So it's waiting here. This is waiting for some seconds. That is mentioned. Okay. So now let's see. So at this point, the execution was waiting for some time. So if you see here, when the program 1 ran, it printed the print that was present in the program 1. So parent executing before wait. Child process created by parent is 11439. So 11439 is the process ID of the child that is created by the parent. So this is coming from this line. Let's see this. This is the one. So in the else part, the parent executes and we see this. So after that, the parent sleeps for 2 seconds, and when it sleeps for 2 seconds, meanwhile the child is being created and the new program 2 starts running. And if you see here, the program 2 starts running from this point. So I am a new process called by SIGKILL. my new program ID is 11439. So this is the child's process ID. And if you see here 11439 and this is same. So in the parent process, the process ID of the child and the process ID in the program 2 are same. Now these are the arguments. This is of just for reference purpose. Now if you see this, caught sig user 2 in child. So after sleeping for 2 seconds, the parent wakes up, the parent process wakes up and sends a signal called as sig user 2. So sig user 1 and sig user 2 are the user defined signals and these are not generated by the kernel. So now the parent process sends a signal sig user 2 to the child, and this, the child process which was running, maybe it was sleeping for 5 seconds here. So when it was sleeping for 5 seconds here, meanwhile it got a signal called as sig user 2 and it would have jumped to this line and this line is printed. Yeah, this is what we can see here, caught sig user 2 in child. So this print is coming from here. So whenever a signal is sent from the parent to the child, after handling the required signal, it jumps to the signal handler and executes the code specified in the signal handler. Now if you go forward, we can see sending sig user 1 to parent. So now after sleeping for 5 seconds, child is about to send a sig user 1 to parent, and now it sends to the parent's process ID. That is, get ppid specifies the parent's process ID and sends sig user 1. Now the sig user 1 is being handled here. So since the sig user 1 is being handled in the parent, for example, let's see this. This is the handler of sig user 1. This is because we have given the signal system call and handled the sig user 1. After receiving sig user 1 in the parent process, it prints this line. So this line is coming from the parent process. If you see here, parent caught sig user 1 in parent. Then later child exits. After sending the process signal to the parent process, it will sleep for 10 seconds and exits. After exiting, the parent is in fact waiting for the child here and it collects the exit status, and then after the child exits, the parent process prints these 3 lines. That is nothing but these. So it prints this line and it prints the process ID of parent, and it prints the wait. The wait returns the process ID for which it was waiting. That is nothing but the child process ID, and the parent in the parent the status is 0. So since it returned 0, the exit status is 0 here. So by this demo, we can see how the user defined signal can be sent between related process, or like between a child and a parent process. So in turn, this sig user 1 and 2 can be used for synchronization between the process.